Good morning, students. In this video, we are going to study regarding the design of flanged beams. In the previous videos, we have studied design of singly reinforced beam, design of doubly reinforced beam. Next is we'll study now design of the flanged beam. Already in the earlier videos, we have studied regarding the analysis of flanged beams and we have covered all the cases. So now let us try to see one design problem. So let us start with the problem now. So we have one question, that is we have one T-beam slab floor of an office which is having a slab of 150 mm thick. So slab thickness is 150 mm, that is nothing but the depth of the flange. So if you take this as the slab and beam what we have, T-beam. So this thick depth of this slab is 150 mm we have, 6 inches. Spanning between the ribs spaced at 3 meters center. So for example, if you take this beam itself continuous, what happens is that it will be somewhat like this. Right? So another beam we have. So spacing between this is 3 meters. 3 meters we have. Then next is the effective span of the beam is 8 meters. Effective span of the beam is 8 meters, that is L is equal to 8 meters, and spacing of T beams is 3 meters center to center. This is 3 meters and perpendicular to this length is 8 meters effective span. Live load on floor is 4 kilonewton per meter square. So live load is 4 kilonewton per meter square we have. So we are going to use M20 grade of concrete and Fe415 steel. So now we have to design one intermediate beam. So for example, what happens is if you see, so and if you are going to have, it will be acting as a L beam. So intermediate if you have, then we are going to design it as a T beam. So therefore they have given in the question, we have to design it as a intermediate beam. So let us solve now with this data. So first what we have to do is that we have to fix the dimensions of the beam. So for example, if this is the beam what we have to fix the dimension. What should be the width and what should be the depth, overall depth what we have. So now how we are going to fix the overall depth of the T beam. So we can assume D is equal to approximately, that is equal to 112 to 1/15 of the span. So now span is how much? 8000. So therefore capital D is equal to 8000 divided by 12 to 8000 divided by 15. Somewhere in between these two values we will try to fix the depth of the T beam. So if you calculate 8000 by 12, it will be 666, or 8000 by 15, it will be 533 mm. So what we can do, somewhere in between these two, we can assume one value, that is we'll assume overall depth that is equal to 600 mm. Then next, if you remove effective cover, so if you take effective cover as 50 mm, so effective depth will be 550 mm. Then next, we can assume the width of the web, so that is taken approximately 1 by 2 to 1 by 1/3 of the depth of the beam. So therefore we can assume the width of BW width is equal to 300 mm. Then next is we have to calculate the width of the flange. So already this formula already we have seen in the analysis part, that is width of the flange BF is equal to L0 divided by 6, where L0 is nothing but the effective span, BW is nothing but the width of the web, and 6 times of df, that is depth of the flange. So L0 by 6, L0 is 8000 by 6, then BW is 300, df is nothing but depth of the flange, that is 150. If you simplify, we will get answer as 2533 mm. Then next another criteria is, or we have to calculate bf is equal to 0.5 times of L1 plus L2 plus BW. So out of these two we have to take the least value. So 0.5 we have, span is nothing but it is spaced at 3 meters interval, that is equal to 3000. So next is we have to subtract 300 mm. So L1 is equal to L2. So therefore it will be 2 times of what you can say 3000 minus of 300 plus BW. BW is 300. So therefore what we can do is we are going to get answer as 3000 mm. So we can adopt the least of these two values, that is BF is equal to 2530 mm. That is nothing but the width of the flange. Then next is we'll go with the load calculation. So what happens is that when we are going to have two beams, so for example if this is the beam we have, this is continuation part I'll show. Then next is we are talking about this beam and this beam. Whenever you want to design this beam, so what happens is that we have to calculate what is the load coming from this slab, what will be transferred to this beam, that has to be calculated. So therefore first let us try to calculate the self weight of the slab. So slab thickness is 150 mm, that is 0.15, multiplied by density of concrete. So this is meter, so multiplied by this is kilonewton per cubic meter. So therefore this will be gone. So therefore remaining will be kilonewton per meter square. So if you multiply, you'll get unit as kilonewton per meter square. Then next let us assume a live load of 4 kilonewton per meter square. So why we are assuming 4? So it is because in the problem they have given it as a office building. So therefore for a given office building we'll assume live load as 4. If it was a residential building we would have assumed it as a 2 kilonewton per meter square. This is 4 we have. The next we'll assume the floor finishes as 0.6 kilonewton per meter square. So if you are going to add up all these values, we are going to get answer as 8.35 kilonewton per meter square. Then next is we'll try to calculate load from slab to the rib what we have. So 8.35 we have multiplied by the spacing, that is 3. So therefore 25.05 kilonewton per meter square we have. Then next let us try to calculate the self weight of rib. Self weight of this rib. So for example if this is the rib what we have, this self weight of what you can say this rib we have to calculate now. This rib we have to calculate. So its width is how much? This width is zero point 0.3 we have multiplied by this depth we have. So if you see 0.3 we have, 0.3 we have, that is width. Then next comes is depth. So how do you calculate depth now? Overall depth is 600 minus of we have to remove 150. Then next remaining depth what we are going to get, that is nothing but the depth of the rib, that is 0.6 minus 0.15. So multiplied by density of concrete 25 kilonewton per meter cube. So if you multiply you'll get answer as 3.375 kilonewton per meter we are going to get. Why? Because this is density kilonewton per meter cube multiplied by the area. This is meter and this is meter. So therefore unit lastly remaining will be kilonewton per meter. Then next is if you are going to add up this 25, that is the load from the slab to the rib as well as the self weight of the rib. So that is 3.375. We'll get answer as 28.425 kilonewton per meter. Then next we'll multiply this by a factor of safety, that is 1.5. Therefore factored load WU is equal to 1.5 multiplied by 28.425. So therefore we'll get answer as 42.6 kilonewton per meters. Then next is we will try to calculate the bending moment and shear force values. So bending moment, we know the formula is WL square by 8. So W is nothing but the ultimate load what we have, that is 42.06 multiplied by 8 square divided by 8. So we will get answer as 340 kilonewton meter. This is the bending moment. Then next is we will try to calculate the shear, that is VU is equal to WU into L divided by 2. So WU is 42.05 multiplied by 8 divided by 2. So therefore we will get answer as 170 kilonewtons. Then next is we'll try to calculate now the moment, limiting moment. So let us assume now the depth of the neutral axis, that is XU is equal to DF, that is depth of the flange. Whether this depth of the neutral axis, whether it is going to lie in the flange or web. So first let us assume whether it is assume that so depth of the neutral axis is lying within the flange, that is 150 mm. So moment is equal to, already we have seen this formula, 0.36 fck into b into xu into d minus 0.4 to xu. So instead of this xu, so we will substitute value of df. Instead of xu we will substitute df. Why? Because we are assuming x is equal to df initially. 0.36 fck is 20 we have, width of the flange that is 2530, depth of the flange it is 150, into bracket of d is 550 minus of 0.42 or 0.416, df is nothing but 150 we have. So if you simplify we will get answer as 1332.3 kilonewton meter. Then next if you compare this with the mu, if you compare this with mu, we have 340. So mu is less than mu1, so therefore what we have assumed is right, you can say, therefore the neutral axis lies within the flange. Now for this we will try to calculate the area of steel. So area of steel is equal to, already we have seen this formula, that is 0.5 into fck divided by f of y into bracket of 1 minus square root of 1 minus 4.6 into mu divided by fck bd square into b into d. So instead of b we have to use bf. So now here in this we'll try to substitute now. 0.5 fck is 20 divided by f of y is 415, 1 minus square root of 1 minus 4.6 into mu is 340 into 10 raised to 6, so as to convert it from kilonewton meter to newton mm, divided by fck into bf, that is 2530 into d square, that is 550 square, multiplied by bf, that is into d, 2530 multiplied by 550. So therefore area required will be 1760 mm square. So as to what we will do, let us assume now 20 mm dia bars. 20 mm dia bars, if you calculate area of 20 mm dia, that is pi by 4 into 20 square, so that will be equal to 314 something we'll have. Then next we will try to calculate number of bars. So number of bars will be equal to 1760 divided by 314. So approximately we are going to get it as 6 bars. So therefore we can use 6 bars of 20 mm dia. Therefore we can provide 6 bars of 20 mm dia. So therefore AST provided will be equal to 1884 mm square. Then next we will check for shear, and we'll check for deflection also. So let us check for shear. So we'll try to calculate tau v, that is equal to vu divided by b into d we used to have. So instead of b bw we have, so vu is 170 into 10 raised to 3 divided by 300 into d is 550. So we are going to get 1.03 newton per mm square. So that has to be checked with tau c max. So tau c max maximum value is 2.8. So therefore this is less than what you can say tau c max. So therefore we can proceed now. So we will try to calculate the percentage of steel, that is AST by BD multiplied by 100. So AST provided is 1884 divided by B is 300, D is 550 multiplied by 100. So therefore we'll get answer as 1.14 percentage. Then next we'll try to calculate as per IS 456 2000, that is table number 19. So we have to calculate the value of tau c. So therefore this value of tau c will be equal to, you can see here now. So our percentage of steel is 1.14. It is what you can say 1.14 somewhere here we have to have, and we have M20 grade of concrete 1.14 somewhere here we have. So it will, the values will be between 0.62 and 0.67. So therefore it is approximately 0.65 newton per mm square. We have to interpolate and we have to get the values, that is 0.65 newton per mm square. And tau v has to be checked with tau c value. Tau v value is 1.03, which is greater than 0.65. Tau v is greater than tau c, so therefore we have to design it for shear now. So we have to calculate VUS, that is equal to tau v minus of tau c multiplied by BD. So that is 1.03 minus of 0.65 multiplied by 300 multiplied by 550. So we'll get answer as 62,700 newtons. Then next, let us assume 8 dia bars. So area of one bar, that is pi by 4 into 8 square, it will be 50. 50 we have, multiplied by, as it is a two-legged, so multiply by 2, so therefore we will get area of this stirrups, it will be 100 square. Then next is the spacing SV will be equal to 0.87 f of I into ASV into D divided by VUS. Already all these formulas already we have covered. So just only it is like repetition for us. 0.87 f of Y is 415, ASV is 100, multiplied by D is 550, divided by VUS, that is 62,700. So therefore spacing will be 316 or we have to check it for 0.75 D. So that will be equal to 412 or 300 whichever is least of all these values, that has to be provided. So 300 is the least value, so therefore we can provide two-legged 8 dia about 300 center to center. Then next is we have to check for deflection now. Already we have seen this formula, that is LD L by D max, that has to be equal to L by D basic multiplied by F1, F2, F3 or KT, KC and KF we are going to have in the code book. So F1 is for tension, compression and flanged beams. So we have to calculate now percentage of steel. Already we have calculated, which is 1.14. So therefore from figure 4, that is of IS 456 2000. So you'll come to know. So you can see now. Here we have, based on this modification factor for tension steel, we have this formula, that is 0.5 into FC F of Y. Here you can see 0.58 F of Y multiplied by area of cross section steel required, that is 1760 divided by AST provided 1884. So you'll get answer somewhere as 225 Newton per square. So we know the percentage of steel. Percentage of steel is 1.14. That is 1.14 means somewhere here we are going to get. So here we are going to get, and Fs value is 225. So therefore somewhere here we are getting those values. If we come somewhere here, it is approximately equal to 1 itself. So therefore what we can do, we can write it as F1 is equal to 1. Then next is F2. F2 is for compression reinforcement. So we have not provided any compression reinforcement. Therefore F2 is equal to 1. Then next is we will go to the third value, that is F3. It is for a flanged section. So for flanged section, if you see here they have given, that is reduction factor for span to effective depth for flanged beam. So for that we have to calculate ratio of web width to the flanged width. Web width is 300, this is not 3000, this is 300 divided by BF is equal to 2530. So therefore this will be equal to 0.118. So here 0.118 means somewhere here will come, will have, so if you go at the top it will be nearly equal to 1 itself. So therefore F3 will be equal to 1. So in that formula we'll try to substitute L by D max is equal to 20 multiplied by 1 1 1. So therefore this will be equal to 20 itself. Then next we'll try to compare with L by D actual, that is L is 8000 divided by D is 350. So it is 14.54, which is less than what you can say 20, that is L by D maximum. So therefore this is safe. So in the previous problem we have checked for deflection as well as shear. Next is you can take this problem as an assignment question. You have to solve this and you have to submit it later. So you can take screenshot of this and you can try to solve the problem as a assignment question.